So we'll have a magnetic field here. It depends on whether which one is the North Pole. If this is the North Pole, this definitely becomes the South Pole according to what I've drawn there. Alright, so identify the components A and B on fig 8.1. So A is just the carbon brushes, right, and then B slip rings. Okay, right, now the next component, okay, component C is made of soft iron. Describe the effect of this component on the generator. Right, this will increase or strengthen. This strengthens the magnetic field. Right, iron is a ferrous material, remember that, so it's easily magnetized. So in this case, is going to increase or strengthen the magnetic field there around that coil. Right, what's the next thing? Sketch. Right, the coil of the generator rotates at a constant speed. Of course, is rotating at a constant speed of 2 complete revolutions per second. Sketch a graph of the EMF generated against time on the axis in fig 8.1. The coil is in the position shown, right? So it's very key to capture those things. So when t is equal to 0, the coil is in that position. So the moment the coil begins to rotate, it's going to cut through those magnetic field lines. Okay, so we can start from a maximum at t equal to 0, and then a minimum at probably 0.5, 0.25 if you go back to the graph there. Alright, so the graph will look like this. It's a sinusoidal curve. It could be a graph of cos, or maybe to some extent a graph of sine, depending on what equation we use from the magnetic flux. But I'll assume that it was the graph of sine from the magnetic flux, and then now we have a graph of cos. So up here, I'm going to plot a point there. That's maximum at 0. Then we'll have another point down here. Then a minimum down there all the way up there. This is what we have. And then up there. So the graph will look like this. Right. Right, of course, don't mind me there. So yeah, there's a complete revolution for 2 cycles. 2 cycles there. Alright. Sinusoidal curve. In power stations, the transformers are used to step up the voltage of electricity generated before it is transmitted through cables over a long distance. Explain the advantages of transmitting electricity at high voltage. I've seen this question several times. So the reason why electricity is transmitted at high voltage, this is to reduce power loss. So there is less power loss for the same power transmitted. So that's the first point that you have to highlight. Less power loss for the same power transmitted. That's the first thing that you need to highlight. Why is it like that? It's because of this guy. Because, maybe you can put a comma there and say because power is equal to current squared R. Okay, power is equal to current squared R. So low current for the same power transmission, it means we'll have to maintain So low current can be used for the same power transmission. Right, and what does this imply? It implies that we can also use some thinner or cheap cables. Thinner or cheap cables. Okay, now let's move on to the next one. Yeah, you can highlight those things on that kind of question. Right, a power station generates electricity at 25,000 volts. A transformer steps up the voltage to the 300,000. The primary coil is that, and there's 450 turns. Calculate the number of turns. So here is the idea of just remembering that voltage and number of turns are proportional. Okay, so ns is proportional to vs. So you can have vp down here and np down there. It will flip when it comes to the other things like current. Okay, then from here we can substitute, right? vs is how much? That's the secondary, 300,000 divided by vp, that's 25,000. Right, this is equal to ns over np, which is 450. Of course these guys will cancel out. Then we have 300 times 450 divided by 25. This will give us ns. So if you use your calculator there, you will get 5,400. ns is equal to 5,400. 5,400 tens. Right, I hope we got this right. Okay.